Welcome to section 4.5. We're going to continue by talking about vector spaces by adding a little detail, and that's what's known as the dimension of a vector space. This is actually one of the reasons that we wanted to find the basis in our previous section. So I'm going to mention some important theorems, then I'm going to get to the dimension. So first theorem is that a vector space has a basis, and any set in V contain more than the number of vectors in the basis must be linearly dependent. That actually means that, here's another way to think about that. That means the basis, the number of vectors in the basis, is the smallest number of, or the largest number of linearly independent vectors in the space. Well, that theorem is followed up by this. If there is a basis with n vectors, then every basis consists of exactly n vectors. So that means all bases of a vector space have the same number of vectors. And this is where we get dimension. So dimension is denoted dim of V is the number of vectors in a basis. Remember, that's any basis. All bases have the same number of vectors in them. So the dimension of the zero vector is a very tricky one. It's 0. And that's because the basis is the zero vector, but the zero vector is technically not linearly independent, so we don't worry about it. Every other vector space, besides the zero space, is spanned by a finite set. We call it finite dimensional. On the other hand, if it's spanned by it's not spanned by a finite set, then it's infinite dimensional. Now, in this class, we are going to focus on finite dimensional, but there do exist things that are infinitely dimensional, and that's where it gets a little bit tricky. And that's a whole different area of mathematics, and it's way beyond the scope of this class, but I am going to put it out there because it is out there. All right, so let's talk about the dimension of a specific subspace. So let's look at this space that's made up of vectors that look like this. Because for some A, B, C, and D that are real. Well, remember that we can rewrite it then as being spanned by these 4 vectors right here. So these 4 vectors span my entire set. Now, we know that that is a spanning set. To find the dimension, all we have to do is find a basis. So remember, basis is a linearly independent set that spans. A spanning set. So we have a spanning set. Is this linearly independent, this spanning set? The answer to that is actually no. Now, just a quick observation, you'll notice that these 2 vectors are scalars of each other. So I can actually get away with deleting one of these vectors. In this specific case, I can delete this vector right here, and I still have a spanning set. So I can just pick the other 3. Now, if I take those 3 and I put them into a matrix and did row reduction, we would quickly notice that they only have 3 pivots, that they're all linearly independent. So it turns out that this is our spanning set. And that's also linearly independent, so it's a basis. So for this reason, the dimension of this space is 3, because it can be spanned. The smallest spanning set of this space is a set that has 3 vectors that are all linearly independent. So this is an optimization and minimization kind of a problem that really is kind of useful, a different way to think about it. All right, so that's example 1. Let's do another small example. Well, I almost forgot, throw this there. This is actually kind of an important one. Any subspace, the dimension of any subspace is less than or equal to the dimension of the larger vector space. Now, this is only true for finite dimensional, but again, that's what we're focused on in this class. So let's think about this for a second. If you have a set of, I'm going to go back to the previous example. Notice that each of these vectors is part of R4. Let me change my writer. It's part of R4. Well, the dimension of R4 is 4. That's why it's called four-dimensional space. So I knew that my dimension of this subspace had to be less than or equal to 4, which we just showed that 3 is less than or equal to 4. So we're completely good in this case. Now, so that's what this theorem is trying to tell us. So that actually means we can leverage this. Anytime you're dealing with something, you can always use that to kind of check yourself here if you're even in the general ballpark. All right, now here's another really important theorem. If I have a space that is a p-dimensional space, so p is bigger than or equal to 1, so it's not an empty space, vector space. It's not just the zero vector. Any linear independent set of p vectors in V is automatically a basis. And any set of p elements that spans V is automatically a basis. So that means if the dimension is, let's say, 5, if I can find 5 linearly independent vectors in that space, then they are a basis. If I can find 5 vectors that span it, that's a basis. So if you know the dimension, all you have to do is find 5, that number of things that either span it or that are linearly independent, and you automatically have leveraged yourself into a good spot. All right, so let's find the dimensions of the null space and the column space of this particular matrix. Now remember, this matrix is a 3 by 5 matrix. Now we mentioned that the null space of this matrix is inside, and I'm going to use this as the inside notation, R what? This is a good reminder. Well, it's within R5. So that means that the dimension of the null space of A is going to be less than or equal to 5. So we get this by that last theorem, we automatically know that it's less than or equal to 5. Similarly, we know that the column space lives within R3. Now you could say for the column space, you can always say a spanning set of that are all the columns. But that's not going to give you the minimum set. So again, how do we find the null space and how do we find the column space? What we did before is we did row reduction. So go ahead and take a minute and reduce this matrix to reduced row echelon form. Go ahead. All right, so if you reduce it to reduced row echelon form, we're actually going to use some things to our advantage here. Let's just look at this for a second. This is actually the example we did in a previous section, and you will again notice I have 2 pivots, right? Well, those pivots are going to be my columns that I pick in the original matrix for my column space. So C of A, we often write that as the span of the matrices, the vectors -1, -3, 1, 2, and -1, 2, 5. All right, so this is it. Now, this set, it turns out that because of the row reduction we already did, we know that this happens to be the smallest spanning set of this column space. So because we already did row reduction over here, we automatically know that this right here happens to actually be the dimension. And the dimension is 2. Well, that's pretty nice. So knowing that the dimension of the column space, that's not pretty. Is equal to 2, we can then ask the question, what's the dimension of the null space? So again, I don't need to actually write down what its spanning set is. I can ask how many free variables. There's going to be 3 free variables, which means the dimension is going to be 3. So the column space and the null space we can leverage in this manner to figure out how many items we actually end up having. So, and if I just click into the next step, again, I have 3 free variables, that's the null space. I have 2 pivots, so the dimension of the column space is 2. So the dimension of the column space and the null space are really nice and easy because all I have to do is, I didn't even have to get to reducer echelon form. I just had to get to row echelon form, and I can use that to figure out the pivots and the free variables. Now, this is not going to say that right now we can easily pull out the null space. We can the column space, but the null space usually takes a little bit more. All right, so that's the end of this video. I hope that kind of sets you up. I'm going to give you another little trick in the next section to help you out to understand all of this a little bit more.